Hi everybody, I'm here to just give you a little recap about matrices, because it might have been years for you since you've done matrices, and some of you have taken linear algebra, so this is just a boring review, so feel free to tune out if you've learned this stuff, but if you haven't, this is going to be a good review. So let's say we have a matrix M, and let's say that it's an n by n square matrix. Okay. So this matrix M can be represented as a function of like the index of the rows and the index of the columns. So our first element is going to be M11, and our last element is M n, because this is an n by n matrix, right? So how does the indexing actually work? So it goes rows and then columns. So some of you might know this as RC. So the way I like to think about it is rows and columns. Rows sort of sounds like roads. So if you think about like some sort of old town or something like that, chances are there were some little roads or paths before there were columns built in front of a house or something. So your own stupid little device to remember how that works. Okay, so if we note that it's the rows and then the columns, this is going to be M21, and this is going to be M12. And then all the way over to M1n, and then all the way down to M n1, and then all the way over. And this, of course, would be M22, and then all the way down the diagonal. So hopefully that makes sense, the basic structure of a matrix. So the same exact thing happens in multiplication. It's the rows and the columns. But we're actually going to focus on addition. So let's just suppose that we have two matrices, big A, that looks like, let's go with 1, 0, 0, 1, and B, we're going to say that's 1, 2, 3, 4. Now when we add these two together, A plus B, we get 0, 1, 1, 0 plus 1, 2, 3, 4. Gives us 1 plus 1 is 2, 2 plus 0 is 2, 3 plus 0 is 3, and 4 plus 1 is 5. So then we get the matrix that looks like 2, 2, 3, 5. Now what if we multiplied those two together? So A times B. So this is, again, 0, 1, 1, 0. Just 1's on the diagonal there. And 1, 2, 3, 4. So how do we find out this spot, for example? So we're going to use the row column thing that I talked about earlier. Remember RC? So we get this row times this column to give us this spot. All right. So 1 times 1 is 1. 0 times 3 is 0. So we just get 1. Now for the next spot here, it's going to be this row times this column. So it's 0 times 1 and 1 times 3, so we get 3. And then for the next one, it's going to be the first row times the second column. 1 times 2, 0 times 4 gives us 2. And finally, the last spot gives us 4. And notice that this is B. So this matrix, let's even switch colors because this is important. So this matrix is the identity. So specifically, this is I2. It's the identity that's the 2 by 2 matrix. So, so whenever we multiply the identity matrix by another matrix, we get that same matrix back. So I guess we can call it even a theorem if you'd like. So theorem, so let's say we have an n by n square matrix A, then we have that IAN is equal to A is equal to IN times A. So no matter which side we multiply that identity on, we're still going to get A back. So hopefully that makes sense. So that's an example of multiplication with the identity matrix. Now what if we consider like a column vector? So what is a column vector? So I guess we'll call this a definition. So a column vector is a matrix. So there's just one column. So it's an n by 1 matrix, for example. So if we considered a matrix B, this is going to be B1, B2, all the way down to Bn. So column vectors are pretty important in the world of quantum mechanics. So definitely get familiar with using them. Alright, so if there's a column vector, naturally there's a row vector. So row vector is a 1 by n matrix. So if we had a matrix C, this looks like C1, C2, C3, all the way to Cn, for example. So it's going to be just n elements. So there's only one row. And with a column vector, there's only one column. Okay, so we talked about like basic matrix addition and multiplication. So now we're going to move on to something a little bit more, slightly more difficult. So we talked about the identity. There are also inverses, so you can find an inverse of a matrix, but we're not going to necessarily talk about that right now because it's not extremely vital. Now we can do one more thing. It's called taking the transpose. So if we're taking the transpose of a matrix, let's say the matrix element is Aij. So again, Aij is the element. So would I be the row or the column? That's right, it's the row, because remember RC. So J is going to be the column. So in the transpose, the rows and columns flip. So this becomes AJI. So essentially, we're going to say the rows switch with the columns. And for the matrix A, the transpose is AT. So let's see an example of this. So if I gave you the matrix B, which is a 1, 2, 3, 9. Ha, you thought I was going to put 4, and I put 9. So what's BT? B transpose. So if we interchange the rows and the columns, everything on the diagonal is going to stay the same, right? So that row that was originally 1, 2 is going to become the column 1, 2. And the row that was originally 3, 9 is going to become the column 3, 9. So that's what taking the transpose of that matrix looks like. Alright, so next up we're going to talk about determinants. So given a 2 by 2 matrix, let's say the matrix that looks like M is equal to A, B, C, D. The determinant, or det of M, sometimes this is denoted with like sort of like the hard lines on the end. It's just a scalar value that we get back at the end. It's not a matrix anymore. So when we take the determinant, let's take a second to think if you remember what a determinant is. Alright, I think I gave you a second to think about what that determinant is. So this determinant is equal to the values multiplied on the diagonal and subtracted on the anti-diagonal. So pretend if you have your right hand and you're doing disco moves, like up to the sky, that disco is the anti-diagonal. So that disco is CB, for example, and the diagonal is AD. So we're going to have AD minus BC. So if you had a 3x3 matrix, sometimes you'll rewrite this as AB, CD in brackets, by the way. So if you have a 3x3 matrix that looks like A, B, C, D, E, F, G, H, I, the way you calculate the determinant is using minors. So what a minor is it allows you to sort of break up a matrix into different parts. So here's how we're going to do it. Let's even switch colors to blue. So we want to find the determinant of M. So we break this up into 3 parts, okay? So when we're finding that minor, what we do is we take this element and we cross off that column and cross off that row. So we're left with like a little matrix on the inside, okay? But this is the determinant, so we have E, F, H, I. Now when we're doing this sort of process, the sign alternates back and forth. So now we have B, we're crossing off that row and column again. So we have minus B, D, F, G, I. And finally we're going to have plus C, D, E, G, H. Okay? So now we have just a bunch of small determinants to take, right? So this is A times EI minus FH minus B times DI minus FG plus C times the quantity DH minus EG. And again, we can just multiply this out even further. So we have AEI minus AFH minus BDI plus BFG plus CDH minus CEG. So that's what the determinant of a 3x3 matrix is. And as you can see, this process becomes a little more difficult for larger matrices. So we're going to take a look at some strategies that we can deal with when looking at these other matrices. Okay, let's say we have the following matrix that looks like this F matrix. This isn't something obvious that you might not know, but it's a little trick to make finding the determinant slightly easier for larger matrices. So if you have this 4x4 matrix F, this is called the, let's see if you can guess it. You probably won't guess it unless you have taken linear algebra already, but it doesn't hurt to give this a shot. That's right, it was right on the tip of your tongue. This looks like a triangle, so this is called an upper triangular matrix. Again, this probably isn't the most useful for this, but if the matrix is in this form, which often enough it probably won't be, the upper triangular matrix, there's a theorem that says the determinant is just the multiplication of the things on the diagonal. So the determinant of F, for example, would just be F11 times F22 times F33 times F44. So if this matrix was a lower triangular matrix, which means all the values to the upper right of the diagonal would be 0, the determinant would also be the same thing, multiplying all the elements on the diagonal. And finally, if the matrix were diagonal, let's see an example of that. So that's what we found out what the determinant was for the upper triangular matrix. Now we have this 5x5 matrix G that only has elements on the diagonal, and this is called a diagonal matrix. So again, it's the same strategy as before with this upper triangular matrix. So we just multiplied the elements on the diagonal. So A, B, C, D, E. Now this strategy doesn't work for any matrix. This only works for upper triangular, lower triangular, and diagonal matrices. So if you have another matrix, you might try and get it in this form. Well, anyway, thanks for watching the intro on matrices, and I hope you have a great day. Thanks for watching. Don't forget to be awesome.